Hi, my name is Stein and I am a marketing engineer here at Nexperia. And today we're going to talk about the safe operating area of a MOSFET, or SOA for short. So in an Nexperia Power MOSFET datasheet, this is what a SOA graph will usually look like. It's a logarithmic graph where at the x-axis you have the drain source voltage and on the y-axis you have the drain current. And it's built up of multiple regions. So the first region here, that's when the device is fully enhanced. So that's the RDS unlimited. The horizontal line is when it's ID max limited, so that's the drain current. And the vertical line is the drain source voltage rating of the device. So if it's rated to 100 volts or 40 volts, that's where this line would cut off. Anything under here, that's what we call linear mode. Now any device turning on or any device turning off will have to go through linear mode. Usually that takes in the region of nanoseconds. However, in certain applications such as soft switching or hotswap, that might be extended to tens of milliseconds. And that's where the SOA graph becomes very important. Now to understand where this SOA graph kind of comes from, we can then break it down to a silicon level. And for that we can have a look at the transfer characteristics of the MOSFET itself. And here we see that it's a drain current is a function of the gate source voltage. And with a lower gate source voltage, we have multiple different regions that the MOSFET can be in. So the lower gate source voltage, when we're in linear mode, you have a positive temperature coefficient. What that means is that as current is flowing through the device, it will heat up, and as it heats up, more current will be allowed to flow, as it will go up this line. More current is allowed to flow, heat goes up, it's a runaway effect, and you have a unstable area. Then you have the zero temperature coefficient, as this point here, and then anything over, that's the negative temperature coefficient. That means as temperature goes up, the current through the device goes down. So armed with this knowledge, we can actually see what happens in the silicon itself. So here we have a piece of silicon. It's in profile, so we have the drain down here, we have the gate trenches here, and we have the source up here. Now the way to view these gate trenches is that when they're turning on or off, it's actually a bunch of smaller MOSFETs around each gate trench, which is what we see here. This helps us then to understand that in manufacturing, there will always be some engineering tolerance. And that tolerance means that one of these trenches might have a lower threshold voltage, which means as it turns on, more current will flow through it, and as more current is flowing through it, it will heat up, as we saw here. As it heats up, more current is allowed to flow through it. And again, it's a runaway effect. And that's something we call the Pareto effect. And that Pareto effect is something we can see in the SOA graph. And that's wherever these lines are breaking, that's the Pareto effect or Pareto region of the graph itself. Why this is important is because in a datasheet you'll often see a power rating. So all Nexperia Power MOSFET, they will have a power rating. However, that power rating is steady state and doesn't apply to a MOSFET in linear mode. Now another way to look at this would also be from a silicon perspective. So if we look at it from a silicon die perspective, we have two different effects that can occur. So with a positive temperature coefficient or with a negative temperature coefficient. So the positive temperature coefficient, as more current is allowed to flow through the device, the heat will go up. As the heat is going up, more current is allowed to flow, and you have a hotspot building up where you have a thermal runaway and the Pareto effect is in full swing. Another side is where you have the negative temperature coefficient. So as the temperature goes up, the current goes down and you're inherently in a more stable area and there won't be a hotspot building up. So that explains on a silicon level what's happening here. Now we have the SOA graph here. From a design perspective, or when you actually use a MOSFET, that means that you can select your own drain source voltage, you select your drain current, and then depending on the pulse, as long as you're under these lines, you're safe. So thank you very much for watching. If you have any questions, please go to nexperia.com. Thank you.